Hello everyone. Now let's look at section 6.2, the binomial distributions. So many types of probability problems have only two outcomes or can be reduced to two outcomes. For example, this example we already used a lot of times. When a coin is tossed, it can land on heads or tails. When a six-sided dice roll, it will be either land on an odd number or an even number. In this case, we reduce to like two outcomes. In a basketball game, a team either wins or loses. Situations like these are called binomial experiment. And then we say each repeat of the experiment, it is a trial. So, and we have some requirements, basically 4 requirements for a binomial experiment. Then the first one, there must be a fixed number of trials. So we must know that we have 100 trials or 20 trials. We can also we have infinite, or we don't know what's the trial. And then each trial can only have 2 outcomes, or outcomes can be reduced to 2 outcomes. These outcomes can be considered as either success or failure. It's just a either or. And then it's similar to yes or no. And then the third requirement, the outcomes of each trial must be independent of one another. That means between trials, they don't have influence on each other. And then the fourth requirement, the probability of a success must remain the same of each trial. So success does not imply that something good or positive has occurred. So when we toss a coin, we can define a tail as a success. Then this fourth requirement, for each trial, the probability of landing on tail has to remain the same to qualify for a binomial experiment. And another example, in a probability experiment, we might want to select 10 people and let success represent the number of people who were in an automobile accident in the last 6 months. In this case, the success would not be a positive or good thing, but still we call it a success. The success means something that we focus on. And now let's look at some notations. So the notation for binomial distribution, probability of success, probability of failure, and then P is the numerical probability we have there. We use P to represent that. For example, if we toss a fair coin and then we look at landing on head, then the probability of landing on head will be 0.550%, then that's the P value. And then Q going to be the probability of failure, which is the other side, complementary event. So we use 1 minus P to get the Q. And then N means the number of trials we have. And then X is the number of successes among N trials. So we have 0 smaller than X, smaller than N, and then X can be 0, 1, 2, 3, up to N. So the corresponding possible values for X and their corresponding probability. So that generates a binomial distribution. And then for the binomial probability formula, then in a binomial experiment, the probability of exactly X successes and N trials is going to be using the following formula. We're going to choose X from this N total trials, and then P to the probability of X, Q to the probability of N minus X. Let's see how we can use it. So a coin is tossed 3 times. Find the probability of getting exactly 2 heads. Then this is actually a binomial experiment because it qualifies for the 4 requirement. We have a fixed number of trials. So what is the fixed number of trials? It's 3 times, right? fixed number of trials. So 3 times. And then let's look at the other requirement. Each trial only 2 outcomes. So it's gonna either be head or tail. So no problem. And then the third one, independent. So whether you got head or tails on the first toes doesn't affect whether you got head or tail on the second one. So it is independent. And then the fourth requirement remain the same. It's a fair coin. So P remains same. So no problem. It's a binomial experiment. Then how can we write down a distribution? Then still the same thing, right? We have x, probability of x. This is a binomial distribution, is a discrete distribution. So we can always look at the table format of the discrete distribution. So x, so if you toss a coin 3 times, then you could have no heads. So x can take 0. All 3 tails, that's no heads. You can have 1 head, 2 tails. You can have 2 heads, 1 tail. And then you can have 3 heads. So x gonna be getting heads. So head is now the success we're looking at. And then the probability of success equals little p. That's the setup. And then can we have a 4? No, because we only told n times. Then x cannot exceed n, because you only told 3 times. The maximum you can have is 3. Then we're gonna have we should have all the probabilities listed. That's a complete discrete distribution. Usually we have to do the tree diagram to look at each probability for getting exactly 2 heads. So 2 heads. We want this probability, the probability in this shaded circle here. So we have to do the tree diagram. Then by this binomial experiment setup, we have a formula. We don't have to do that anymore. So we have n choose x times probability to the power of x, and then this q to the power of n minus x. So probability of x equals 2 equals this. Then we know all those information. We just plug in. So that's gonna be truths. We have 3 as the fixed number of trials, n. Choose 2, right? X now exactly, we want exactly 2 heads. And then P, which is 0.5. Fair coin, 50% of landing on head. So that's success. 0.5 to the power of x, which is 2. And then 1 minus 0.5, that's q, to the power of n minus x. That's going to be 3 minus 2. So we can solve this one. So that's going to be 3 choose 2. That's the same as 3 choose 1. And then 0.5 to the power of 2, 0.5 to the power of 1. Then we have 0.5 to the third power. That's 3 times 0.5 to the third power. That's 0.375. 0.375. And then if we want to find the distribution of getting heads, we have to complete this binomial distribution, this discrete distribution table. So we have x equals 0, 1, 2, 3 possible values and probability of x. So for 2, we have 0.375. And then for 1, we have 0.375. So we can calculate this, use the same formula. But we did this before, so we can just write down the answer. 0.125, 0.125. And then add up together, you got sum equals 1. This is the binomial distribution. And now let's look at another table. So this is called the binomial table because for each value we have to apply this binomial formula to calculate the probability. So we can use a computer to calculate every combination that you can have. Then we can now use the table, just check the values. So for example, a coin is tossed 3 times. We want to find the probability of getting exactly 2 heads. How to use the table. So we know the fixed number of trials, n equals 3, and then exactly 2, that means x equals 2, and then the probability of landing on head, because this is a fair coin, we know it's 0.5. So based on these 3 numbers, we can look at the table. So this is for n equals 2, and then 3, 4, 5, 6. So we have different value of x. So when n equals 3, we have x, possible value of x could be 0, 1, 2, 3. And then we're looking at exactly 2 heads. So we want this one and then 2. So now we focus on these row. And then with all different probability of success. So for this specific question, we have probability of success equals 0.5. So this row and then the 0.5 column, we can circle that. The value is 0.375. So this tells us choose 3, 2, p to the 0.5, q to the 0.5, when p equals 0.5, that is 0.375. We can just track the table. And now let's introduce the mean variance and standard deviation of a binomial random variable. So we can always use, when we create this discrete distribution table, we can always use the previous formula to get the mean variance and standard deviation. But since binomial distribution is a special type of discrete distribution, then we have some special formula to calculate the mean variance or standard deviation. So for the mean, it's just n times p. Variance n times p times q. And standard deviation is square root of the variance. So now we can look at this example. So we have mu of x calculated to be 1.5, and sigma squared x calculated to be, let's see, sigma squared equals 0.89. No, the previous one, 0.75. 0.75. Then let's see whether we got the same value using the special formula for binomial distribution, since we know this is a binomial distribution setup. So mu of x equals n times p. So n is 3, we know that already. P equals 0.5, q equals 0.5. So now times 0.5, so that's 1.5, no problem. We verified that. And then for sigma squared, which is a variance, that's n times p times q, which is 3 times 0.5 times 0.5. That's going to be 0.75. So no problem. And then for standard deviation, that's going to be square root of 0.75 as we calculate before. And now let's look at this practice problem. A student takes a multiple choice exam with 10 questions, each with 4 possible selections for the answer. So a passing rate is 60% or better. Suppose that the student was unable to find time to study for the exam and just guesses at each question from the probability that the student will get at least one question correct, receive an A. How many questions would you expect the student to get correct? Obtain the standard deviation of the number of questions that the student gets correct. So this is definitely a discrete distribution problem. But furthermore, let's see whether it is under the special case, the binomial distribution. So first, fixed number of trials, n. So do we have a fixed number of trials? Yes, we have 10 questions. So n equals 10. The second one, do we have 2 outcomes? So correct, incorrect. That's just success or failure for each single trial. So 2 possible outcomes. And then 3, so this is the success. And this is the failure. The third one, independent. Yes. What result you got for one question does not affect the result you got for another question. So independent, check. Then the last one, probability of success. Do we have probability of success? What is the probability that you can get it correct? So it's just the first classical probability rule that we learned. Number of outcomes in these event. If the event equals correct, then you just have one question, and then you have a sample space of 4 questions. So 0.25, that's the probability, and remains same for each trial. So this is no doubt a binomial distribution problem. Then get at least one question correct. Then we can first look at all possible values x can take, and then just draw a table. So possible value x can take starts from 0, so no correct, 1, 2, 3, up to all correct. So 11 different values x can take. So we want to get at least one question correct. So we want 1 question, 2 question, 3 question, 4, up to 10 question, all those. We want that probability. So basically we want to take sum of all those probabilities, which is complicated because we have to calculate 10 times. Check the table or using the formula 10 times. Then we can look at the other way, because we know the sum of the probabilities equals 1, then we just need to use 1 minus probability of x take 0. So no correct. At least one correct, we just use 1 minus no correct. Then it's going to be just one calculation. So 1 minus, choose 10, 0. And then we have p, which is 0.25 to the probability of x. And then q, which is 1 minus p, 0.75 to the probability of 10 minus x. So it's basically anything to the power of 0 is 1. Choose 10, 0, that's 1. So it's basically 1 minus 0.75 to the power of 10. So we can calculate that using the calculator. The power of 10. So that is 0.9437. So basically, the probability that the student gets at least one question correct will be 94%. And receive an A, problem B, receive an A on the exam, 90% or better. So 90%, so got 9, which is okay, and then or 10 correct, which is okay. So probability of x equals 9 plus probability of x equals 10. And then for x equals 9, we have 10 choose 9, 0.25 to the probability of x, 0.75 to the probability of 1, plus choose 10, 10, 0.5 to the probability of 10, 0.75 to the probability of 0. So 10 choose 9 is the same as 10 choose 1, so that's just 10. So we can just use our calculator to get the result. So that's 10 times 0.25 to the power of 9 times 0.75 to the power of 1, just 0.75, and times plus 0.25 to the power of 10, because the rest is going to be 1. Then that is 0.00002. 1, 2, 3, 4, 5. Okay. So which is almost 0. So receive an A or better. Receive an A on the test, 90% or better. That's gonna be 0.0029%. And then how many questions would you expect? So expectation, right? Expectation is the same as the mean. So expected value of x equals n times p, the mean mu of x, right? And then that's 10 times 0.25, which is 2.5. So the student expect to get 2.5 questions correct. That's expectation. And then standard deviation, sigma of x equals square root of n times p times q, which is square root of 10 times 0.25 times 0.75. So let's see what it is. Of 10 times 0.25 times 0.75, and then take square root, which is 1.369. That is the standard deviation. Okay, now we finished the practice problem for this section 6.2, the binomial distribution. And again, don't forget the worksheet 6. It is posted under the lecture folder on Blackboard. Okay, that's all for this chapter 6, and thank you.